All right, welcome. So we spent two sessions kind of drilling into the transformer and in particular looking at from this like circuit point of view that if you imagine the data just sort of flowing from the bottom through the embedder, going through intention layers back to the residual stream, and eventually unembedding, and that gives you the logits for what the next word, the probabilities for the next word. So now that we've kind of looked at the very simple zero layer one, where there's no attention, it's just embedding and unembedding, and looked at the patterns that we have with one layer of attention, we're gonna round out the discussion today by looking at two-layer attention. And this will obviously not tell us everything there is to know about big transformer models, but it will give us sort of this enough building blocks that we can hopefully have some intuition as to the kinds of things that are happening later on. And then I can just mention, depending on the time we have left, some of the other insights that they go through if you want to keep going and look at a little bit more of their papers. So let me make this full screen, and on monitor chat, give me a shout if the audio or the video doesn't look good, and then if, as per our usual, just let us know if we want to pause, discuss, ask a question.
Some success trying to understand one-layer attention-only transformers. And so in this video, we're going to move on and try to study two-layer attention-only transformers. Now, this first video on that topic is going to just be about some theory that we need to build up to do that. But I think it is really quite worthwhile. I found that the ideas that we can build up studying two-layer attention-only models really actually give us some useful traction on thinking about transformers more generally. And we'll also, when we in the video following this one, get to the point of actually empirically studying what's going on inside these models, we'll find a bunch of things that seem to be really important mechanisms that exist in transformers of all sizes and without any of the simplifications that we're using right now. And so I think it's pretty interesting to study these. So recall that in the previous videos, we developed a pretty nice equation for describing transformers. We were able to go and describe them in terms of, well, first we have this direct path term that corresponds to this path here, and then we have these terms corresponding to attention heads, which correspond to all of these paths. And we found that there was a really nice interpretation of both of these. This could sort of be seen as being something like bigram statistics. And this term here tells us if an attention head attends to a particular token, what is the effect on the logits? And this tells us, where the attention head attends. So that was pretty useful. And another way that we could write that is we could say, well, we could put it sort of in a factored form. We could say, well, okay, the first thing you do is you multiply by WE, so first to embed, then we apply the attention heads, and there's the identity path as well, and then finally we do the unembedding. Okay, so once you've done that, it's pretty easy to generalize it to a larger model, or to a model with more attention layers. We're just going to have multiple copies of this term, basically. Now, you might have noticed that every time we talk about WO, it always comes with WV and vice versa. And every time we talk about WQ, it always comes with WK. And because these equations are going to get a little bit larger and more complicated, for simplicity, we're just going to introduce these terms WQK and WOV that correspond to those products. So that's just a little bit of cleanup before we move on to the equations. Okay, so here we have our two-layer attention-only transformer. So we start by going and applying the embedding. So that's at the bottom here. Then we're going to go and talk about the first attention block. So that's all of this. And within that, we have the identity term that corresponds to this path, and then all of these attention head terms that correspond to these paths. And then we have the second layer attention heads.
For just $67, you can make as many videos as you want, and you never need to pick up a camera.
And then finally, we have our good old unembedding. Now, we'd actually, even though this is sort of an easy way to go and describe it, we'd like to expand this, because expanding it will give us, I think, a more helpful way to think about the actual mechanics of the system. And we're going to take advantage of this really nice property. We sort of implicitly talked about it earlier, that when we have tensor products, and if you're not comfortable with tensor products, make sure you watch the video on the theory of one-layer attention heads, where we talk about these a little bit more. But when we have tensor products like this, the items on one side of the tensor product, and we multiply them, the items on one side of the tensor product multiply together. And similarly, the ones on the left-hand side end up going together as well. This is called the mixed product identity. And it's really actually the whole reason why I decided to frame this series in terms of tensor products. And in the case of attention heads in particular, there's a really beautiful interpretation of this, which is that if you chain, really we're only going to do this when these are attention heads and we're multiplying them together. So if you chain two attention heads together, the attention patterns combine and create a new attention pattern. And the matrices that describe where the attention head is reading from and writing to also multiply together, and you get something that looks very much like an attention head. So that's the reason we care about that. Okay, so now we can write the expanded form of that equation. So we have, first, well, we're going to have sort of three types of terms. So we have the direct path term. And this is, we've seen this term all the way back to our zero-layer transformer. It's a good old friend, and it just corresponds to this direct path down the transformer, and it tends to represent bigram-ish statistics. Some of the bigram statistics will start to migrate into attention heads, but the kinds of things that it represents are similar to bigram statistics. Then we'll have terms that correspond to going through a single attention head, and that could go through an attention head in the second layer, or could also go through an attention head in the first layer. So these are the effects of attention heads. And then finally, we have what I'm going to call virtual attention heads. So virtual attention heads are when you have two attention heads, the composition of two attention heads. And that also has some effect on the output. And so virtual attention heads have this nice property that we just get them through the mixed product identity that we were talking about earlier. So we get this attention pattern. They have an attention pattern of their own, which is the product of the two attention patterns. And they have a OV circuit of their own that describes if they attend to a particular token, what the effect will be. And it's just the product of the first OV circuit and the second OV circuit, or the OV matrices at least. So that's what we had. Okay, so a question you might, stepping back for a second, I think one of the things that's really cool about this is it really allows us to study attention heads in a principled way. So I think a lot of the time, there's been a lot.
Yep. Sorry, quick question. I'm not sure if this is the right place to insert it, but can you back up just a few seconds to that diagram? So the thing that came to mind when I saw this, because the way they are doing these virtual attention heads, presumably that works for however many layers that you might have. You could have virtual attention layers probably for any permutation of those, any combination, right?
Yeah.
But it's ignoring the MLP. You can do it because they're all linear, right? But it's ignoring the MLP contribution.
That's right. We have not talked about MLPs. They will do analysis where they include MLPs in the models they train later, but they never are able to develop a clean math like this once you include the MLPs.
Gotcha.
Because they have the nonlinearity. If it was just two linear layers, then you could, because
Yeah,
it could still be
yeah.
linear, but the nonlinearity just blows up the whole thing.
Yeah.
But
Okay.
since we're paused, I think he's going to talk about it. But basically, the attention, what it says is you are going to do an attention pattern. Okay. And so let's just say we're looking at the seventh token, and the attention pattern puts almost all of the attention on the third token. Okay, 99.9999% of the attention is on token 3. All right. Then what that means is we're going to take whatever the OV weights create, and we're going to add that to the residual stream. So the OV weights from token 3 are going to get added to my current position, the seventh token. Does that make sense in terms of this is the way we're describing an attention head? The left-hand side says which token are you copying data from, and the right-hand side says what data are you copying. So what he's trying to point out, and I think he's going to make this clear, is that the two attention heads, and you already figured out, Roger, it could be 3, it could be 7. It's in the exact same format. It's some kind of attention on the left and some kind of value on the right. It's the exact same. So that's why he calls it a virtual attention head. And I think he's going to make it much clearer, but since we're paused anyway, I'm going to say, so imagine that we had my scenario where the first attention head, token 7, really attends to token 3, like 99.9%, okay? And then we have a second attention head where token 10 attends 99.99% to token 7. In effect, the combination of those two means that token 10 is going to attend to token 3, because it's attending to 7, but 7 is just a copy of data from 3. Okay, so the indirect effect of when you have two attention heads working together is that the attentions sort of chain, but then you have to do something pretty complicated here to say, like, well, the values from the first OV times the values from the second OV. And so this may not be a trivial thing that's happening over there, but the chaining of the attention really is intended in this formulation to be pretty simple, that if the first one attends to 3, then whatever attends to it is effectively attending to 3. Make sense? So that's going to be, like, I think one of the big key insights from this whole transformer circuits stuff.
Oh, so that's what we had. Okay, so a question you might, well, okay, stepping back for a second, I think one of the things that's really cool about this is it really allows us to study attention heads in a principled way. So I think a lot of the time, there's been a lot of papers that I think they're genuinely super cool papers, where people go and study attention patterns, and they're like, we found an attention head that appears to attend from this to this, and maybe like it attends to the subject of the sentence or something like this, or if it's a verb, it attends to the subject or something like that. But it's actually pretty tricky to know. Well, there's sort of a conceptual problem, which is it's very tricky to think about attention heads in isolation. They could be the attention heads could be reading information from other attention heads, and they could be, it might appear that an attention head attends to one token and moves it from and goes to a second token, but it could be that the information it's reading from that residual stream actually came from an attention head that was yet earlier, and that the attention head, the information it moves and writes, that information doesn't sort of, that isn't its final destination. It yet moves on further, and so it's very easy to be, I think, potentially to be confused about this, or at least to worry that you might be being confused about this. And it seems to me that, at least for the attention-only case, this framework resolves that, because if it was the case that the important thing was these chains of attention heads, then those would be the virtual attention heads, and that would resolve all of these, and the individual attention head terms would sort of end up being small, and that would completely resolve it. So that made me really happy, because a thing that I felt very uncomfortable about when when I've seen people talking about transform interpretability for a long time has been this concern about chains of attention heads and whether attention patterns are really important or whether they're just sort of illusions that are parts of a much longer chain and that we're missing the whole story. And it feels really good to have a framework that puts us on steady ground with respect to that concern. Okay. So in our next video, we'll be able to go and actually start studying these.
Helen Hansel was able to win any competition she took part in. She was known as the contest queen.
In our last video, we found that we could describe two-layer attention-only transformers with a kind of handy equation. And the equation is three kinds of terms: the direct path terms, the individual attention head terms, and the virtual attention head terms. And something that might be useful to know before we spend a lot of time trying to go and really understand the behavior of the model is how important are those different terms. And it turns out we can actually just explicitly measure that. And so that's what we'll do. So for the direct path term, which is just going straight up down the middle, if you're measuring relative to just making random predictions, you reduce the loss by 1.8 nats when you add that term to the model. So that's a pretty nice drop, especially just for a single very simple term.
Can we stop for a sec?
The individual.
Yep.
Okay. Just because I'm stupid, what's a nat?
I was worried you're going to ask that because I can't answer the question super easily. So, okay. So we all know what bits are, right? So in information theory, you might have heard somebody say that like, oh, we can compress this. This is 5 bits of information or whatever, right?
Right. Uh-huh.
Okay. So bits, I think by definition, if not, then certainly by convention, we're always talking about base 2 information.
Okay.
Okay. But if you're doing natural logarithms, if you're doing base E instead of base 2, okay, then, you know, logarithms, like you can always convert from one logarithm in one base to another base just by multiplying by the ratio of the bases or whatever, the logs of the ratio, the bases. So if you do it base E, the natural log, instead of base 2, instead of bits, you have nats.
Okay. Got it.
And I don't know if it's base something else, 10 or whatever, like what they call it, but so this is a slightly scaled version of bits. But by bits here, we don't mean bits in the literal sense. We mean it in the information theory, information content sense.
Got it. Okay. Thank you very much.
Yep. So then these nats will correspond to, I believe, perplexity, which is something I just can never seem to get my head 100% around. But
So wait, Ted, you're perplexed about perplexity.
yeah, I'm
Okay.
perpetually perplexed about perplexity.
All right. Well, let's move on.
Well, attention heads then, if we go and we add those in on top of the direct path term, so we have the individual attention heads, and they go and give us a reduction of 5.2 nats. Now, since there's 24 terms, it's actually quite a bit less than the direct path term per head. It's only 0.2 nats. But yet they're still doing a lot of work. And then the virtual attention heads, they on top, if you already have the individual attention heads, they only give us a marginal additional 0.3 nats. And because there's quadratically many of these, right? Because for every first layer attention head and every second layer attention head, there's one of these pairs that are the virtual attention heads. So the amount of loss reduction we get per term is very small, 0.002. So probably if we're trying to prioritize what we want to understand, our top priority should be, of course, the WE, which is going to be very easy to understand. It's sort of representing bigramish statistics and gives us a lot of bang the effort. But then we want to study the individual attention head terms probably.
Hey, Ted.
Okay. Now you might wonder, how is it that we?
So my guess would be then that these nats would be for a specific data set, test set. Would that be right?
Yeah, and
I mean-
he's about to describe the method where basically like you train it, and then what do? You run the model, you save all the attention patterns, and then you like zero out part of the signal in order to see how the word predictions get worse. And so if you zero out the straight through path, or you zero out the single one path, or you zero out whatever, and then they like, so I don't think he's going to go into too much detail, but he's going to explain how they calculate, and ultimately that sort of.
And then you average it over the test set.
Yes, I believe so.
Okay, thanks.
Calculated this, and there's kind of a nice algorithm you can use to go and calculate how much these different terms contribute to the loss. And you can use it for this model, but you can also use it for larger models. It scales to potentially very large models. And the trick is, first you just run the model and you save all your attention patterns, because we want to hold the attention patterns fixed. Okay, so you do that. Then you run the model, and you're going to force all the attention patterns to be the attention pattern that you recorded. But instead of adding the attention head outputs to the residual stream, you'll just save them and replace them with 0. So you'll go and record what the attention heads would have added to the residual stream, but then you'll add 0 instead, and you record the loss. So that's just calculating the direct path contribution. Then you're going to go and iteratively run the model. And every time you run it, you're going to force the attention patterns to be the original attention patterns. But instead of going and adding the true output of your attention heads to the residual stream, you'll add whatever you would have added at the previous step that you replaced. And then you'll go and you'll save the output so you can go and add it on the next step. And the nice thing about this is that it means that all of the attention heads only saw at most n-1 attention heads, or sort of were only affected, their values were only affected by n-1 attention heads, at least through the OV circuit, not through the effects of the attention patterns. But if you hold the attention patterns fixed, then that's true. And so that's a way that you can go and understand that. Of course, you could come up with all sorts of variants on this algorithm. So if you wanted to understand how important things were also going through the effects on attention patterns, you could also do that. Okay, so we think that probably we can ignore the virtual attention heads, or at least they aren't our top priority to understand for this model. Now, another question you could ask is, we have really two, for the attention head terms, we sort of have two different things. We have the first layer attention heads and the second layer attention heads.
Most people have no clue that in 2023, the best way to make money on Amazon is not with.
And we can ask, in terms of what is their direct effect on the loss? How much do they affect the loss? And there's sort of two ways you could measure this. One is you could measure relative to there not being any attention heads, or you could measure how much do they add marginally on top of the other heads already being present. So if you want to measure the layer 1 heads, you could either measure relative to the case where there's just no other attention heads, or relative to the case where you've already added the layer 2 attention heads. And to make a long story short, the layer 2 heads have a much larger direct effect than the layer 1 heads. If you measure it in terms of the relative to the direct, or relative to only having the direct path, it's 5.2 nats versus 1.3 nats. If you measure it relative to the other one being present, it's 4 nats versus 0.05 nats. And if you then go and divide by the number of heads, those are obviously getting to be very small numbers for the layer 1. Now, that doesn't mean that the layer 1 attention heads aren't important. they can affect the attention patterns of the layer 2 attention heads, and we'll see that they're doing a really critical job in that. But it means that in terms of this overall equation we have, we don't need to go and worry as much about the layer 2 attention heads. So we can mostly understand the model by understanding the behavior of 12 attention heads. And those 12 attention heads, their attention patterns are influenced by earlier attention heads. But if we understand those 12 attention heads, for instance, you could just empirically understand their attention behavior as a starting point, and their OV circuits, you'd understand the model's behavior. But yeah, it's really important to keep in mind that whenever you see the attention pattern here, particularly not only is it nonlinear, but for later layers, that also contains potentially lots of effects of previous attention heads. And in fact, we can make that explicit if we want. So when we looked at the first layer, the equation for our attention pattern was this. And so it's a little bit complicated, but it's this is the thing that we called our QK circuit matrix, and we're multiplying by tokens on both sides. But when we go and then move to the two-layer model, all of a sudden it becomes a lot more complicated. And what's going on is that rather than just having the tokens get embedded and then affect things, they first go through all of the attention heads in the previous layer, and then they hit the QK matrix. Then the keys also were computed using all of the attention heads, and after they went through the tokens. So on both sides we have attention heads. And if you can expand this all out, of course, and if you want to really analyze this, then you'll have a bunch of terms that involve first layer attention heads going and contributing to the attention pattern. You'll still have something like a QK circuit, but it'll be a bit more complex.
In any case, now that we know what the right terms to focus on are, we're ready to go and explore the model and understand its behavior in our next video.
With the price of just about everything inflating these days, you may wonder why Mint is deflating the price of Mint Unlimited.
Well, we're now ready to actually understand two-layer attention-only transformers. And I think there's actually some really cool stuff inside them, so I'm excited to chat about this. In particular, there's going to be some really interesting stuff that they're doing that kind of is meta-learning relevant and seems to generalize to much larger models. And so hopefully we'll learn some interesting and generalizable lessons. Now, if you watched our previous video on eigenvalue analysis, you'll remember that eigenvalues are kind of a nice way to summarize the behavior of attention heads without having to look at them very closely. And in particular, positive eigenvalues for an OV circuit, for the output value circuit, mean that an attention head wants to increase.
Hey, Dave, I just saw that you have your hand raised. Did you want me to pause?
Oh, thank you, Ted. It was towards the end of the last video when he showed that the attention head equation included contribution from previous layer to the key component of the next layer somehow, or essentially being kind of the key component. And I was wondering, why was it just limited to key and not the query as well? Because I would imagine that those are two components that that get affected. If I visualize the multi-headed layer, multi-layer attention head, then the previous layer is producing new, if you were to interpret the intermediate values, new tokens. So essentially it affects everything, but value I know is going to a different channel, but this is query key channel attention head. So I was just curious, but I don't know if they answer that.
No, you're definitely right. I don't remember what he said exactly in the video, okay? But I can tell you that a lower layer can definitely affect both the keys and the queries. And in fact, the paper goes into a little bit more detail than the videos. So if you look in the paper, you will see that they explicitly Where is it? They go in a slightly different order and they talk about it slightly differently. But basically what I'm trying to look for is they actually use the expressions. Here you can see Q composition, K composition, and V composition. Okay. And so both Q composition and K composition affect the query key patterns at a higher attention layer, whereas V composition has more to do with the data that's actually being copied onto the residual stream. So you're absolutely right. If he didn't say both query and key, definitely he meant to say that because it does affect both.
Thank you, Ted.
The probability of that the output is the same. It'll increase the probability or increase the logits for that the output is the same as the token that it's attending to. So really it just means the attention head is implementing copying. And if last time we saw that really the behavior of our two-layer transformers is mostly described by understanding the second layer attention heads. And there's 12 of those, and of those 12, 7 are doing copying. So it's a little bit less than when we were looking at the one-layer model, but still, the majority of our attention heads are doing copying, and we're going to see that they're doing a much more interesting type of copying and a much more powerful type of copying than the one-layer model was. Yeah, so we could try to go and study this by analyzing the QK circuits. The math would get a little bit complicated. So an alternative is that we can try to just empirically understand the attention patterns. And then we can go from there if we want and try to understand more about the math of the QK circuits. And something that we see a lot of is what we call the induction pattern. So for instance, if we look here, and it might be a little bit hard to read. So let's focus on this D token. So that's the present token. And if we look back, it attends really strongly to ERS, which is the next token after D. And if then we go and when we look at when the present token is ERS, it attends to Li. And this is a very general thing. So, similarly, when the present token is pot. So this is all from the first paragraph of Harry Potter, by the way. I think maybe we mentioned that in a previous video, or maybe we haven't, but I've been having some fun using that as a standard piece of text to go and play around with. But you can also observe this on lots of other text, and it works very reliably. But yeah, so if the present token is pot, well, we have the potters, so we attend to the next token, the token that follows pot previously, TERS. Okay, and so we're starting to get a pretty good hypothesis maybe of what's going on here, which is that somehow this attention head always attends to the token that follows previous copies of the present token. So if we're on pot, the previous copy was pot, and then we get TERS. Okay, so how could it be? Well, that's kind of interesting. Now, a natural hypothesis is that the reason it does that is that it would allow it to go and predict then what the next token is, because the goal of the present token here is to predict the next token. And we can actually just measure that. We can just take the output of the attention head, and it just has a linear path down to the logits. And so we can just run that into the logit. And even without analyzing the terms, we can just see the empirical effect on the logits. And it's indeed going and predicting ERS, going and predicting Li, going and predicting a little bit the pot on Potter. So we have the pot, but then the TERS in Potter is really strongly. And so it's increasing the probability of all of those.
So I just want to check, because he didn't really explain what these pictures are showing. So if your screen resolution is good enough, on the right-hand side, you will see a little gray rectangle around a word, and that's the query word, okay? That's if you're looking at that particular word. If you're looking at nonsense, what is it attending to? If you look at period, what is it attending to? If you look at Mr., what is it attending to? So that's why when he said, like, if you look at the D, what is it attending to? It's actually attending to. So this might be like token whatever 15, and it's attending to token 5, 1, 2, 3, 4, 5. Okay. And so it's this D is attending, has a very large attention score for errors. And for some of these other ones, they're tending to the very first token, and some of them don't have super strong, obvious attention. So where you see dark red, it means that it has one really big attention score for a particular token. And where you don't see bright red, then that means that the attention's kind of just like mixed. It's not super strong. So does that make sense in terms of what these diagrams are trying to show you?
Yeah, what are the first two lines that aren't like highlight, that don't really have any red highlighted?
Yeah, so the word nonsense is actually attending to the first token, the beginning of the sequence. It's not really attending to any particular word strongly. And so
then all it really has to go on to predict the next token is itself, basically, assuming that it attends to itself.
It's not even attending to itself. It's actually attending to like this begin token. So yeah, it really, I would say other than just like general word frequencies, it doesn't really have anything to go on.
Yeah, that's what I was thinking, is that maybe it just relies on the direct path.
Right.
No
Yeah,
attention.
it might rely on the direct path. The attention head is not adding anything. It doesn't mean that there's not some other attention head that's adding something, or the direct path's adding something, but this is just one attention head. This one attention head, when it sees nonsense, isn't really doing anything. But holy cow, when it sees D, it is saying, I am attending super strongly to errors. And when I see errors, I'm attending super strongly to Lee.
Hey, I have a question.
Yeah.
Basically, I was saying that, Harry Potter is such a popular series, so that, in the training of these algorithms, it had encountered a lot of these expressions and such. And, I would think that there's a certain bias that it is able to predict things that it sees out of Harry Potter than it would say, let's say, if you were reading some more, well, if you want to predict some more obscure text, or let's say even like a newspaper, okay? Even though newspapers might also fall into the same trap of being, localized and focused on certain things. But if you take an obscure book, some silly little obscure book, and then try to see, if you can exhibit the same sort of predictive abilities on this, I just really have a lot of doubt whether that could happen.
Yeah, so Walter, I would have to go back and read the exact details in the paper. But if you're following along here, this is a mini pseudo language model. I don't even think it has the linear layers. It just has 2 attention layers. Okay. And they trained it from scratch. So this is not GPT-3 or something. This does not have general internet knowledge. Now they may have actually included Harry Potter in whatever they trained it from scratch, but these are toy examples, and so I think what you're pointing out is valid, but any bias from like Harry Potter showing up a lot probably doesn't really matter as much for their toy.
Okay. I just, I was just, okay. All right, fine.
Yep. Jayanth, you have your hand raised?
Yeah. So I was wondering what's going on with the blue. The darker the blue, the more the logit effect. But
yeah.
Like
so
if
the
you
darker...
look at the third one from the top, the and. So yeah, what I was going to say is that the blue kind of correlates with the red, except in a couple of cases, but I didn't quite follow what the blue is. Yeah.
Yep. They take more time explaining this in the paper. It's actually pages and pages, but that's why I wanted to pause here, because they don't really explain this diagram. So the gray box is the current token position. red to your left, because it always has to be to your left, right? You can't attend to anything to your right in a GPT style language model. So red says what you're attending to, and the brighter red it is, the means it's concentrated on just one token position. It's not spread out. What they also crammed into this diagram is the value that you're then outputting onto the residual stream. The stronger that value is, the darker the blue is on your right. Okay, so because you're always predicting the next token, the blue always has to be immediately to the right of the gray rectangle. It has to be the exact next position. So the only question is it sort of light blue that the word the was actually kind of predicting pot, or pot was really super heavily predicting ters? And then ters didn't really predict anything. It didn't know what the next word was going to be, at least not this attention head. Again, as we said before, there might be other attention heads, there might be the straight through path, but this particular attention head, when it sees ters, it's not really writing very much to the residual stream.
I see. That's super helpful, Ted. Thanks. The only one that I'm having trouble understanding with that information is the first one in example 2.
Mm-hmm.
Why is POT sort of bluish? You have the token I don't see any red on the left, but somehow it's picking up on POT.
Yes, I think we'd have to go into the weights in more detail. So even though you don't see this the attending to one particular token number super strongly, what's possible is that there's sort of a weak signal on token 1 and token 21 and token 50, all the previous like thes, and that's where when you sum them together, you get a slightly stronger pop because it's the same thing over and over again, right? The pink would look like 1/3 as bright as this blue, so it would be hard to see.
Yeah,
and in fact, I think I see a tiny bit of pink on this pot.
Okay.
Tiny bit.
Okay,
It's
don't
hard
see
to see
it
on the
my
video.
display, but yeah, okay.
Yeah. I might be imagining it, but like maybe just a tiny bit. So
okay.
Yes. But
Cool,
that's the
thanks.
purpose of this diagram, is to show you what otherwise would be painstaking for you to like look over all the numbers and figure out and whatever. And so this is really like the cool thing that why I said that this work was so interesting is because there's this really cool induction pattern that says, when you see D, then I know previously in my context, D gets followed by ers. And when I see ers, it gets followed by Li. And so basically, Walter's right. It's possible in the training data, it knows about Dursley. And so that could have been baked into it, okay? But I'm pretty sure people have done this, and even the I don't think it's in the video, but the Anthropic people, they put gibberish in. They just put random tokens in no particular sequence, but they made sure that they were repeated substrings. And the attention picked up on it. So if you just had random like D and then found and then ball, like the found ball is not a word, right? But you repeat that a couple times, and then the next time you see D, bam, it attends and it wants to say found. And then when you say found, it wants to say ball. So I can't remember if it's going to be in the video or not, but they actually did that, where they made sure it wasn't just something from the training corpus by just putting gibberish in.
Ted?
Yeah.
So a quick question on example 2, line 2.
Mm-hmm.
Is the, I can't quite tell on my screen, is the first TERS darker than the other TERSs?
It does look that way. So the attention scores might have been like 0.3, 0.2, 0.2.
Okay.
And it's not like 100%. There could be some attention that's spread elsewhere too,
And am I remembering this? Did this simple model have position encoding? I don't think so, right?
I think they might have had to include it. They haven't talked about it in the math, but I think they had to include it, or else it might not train. It might kind of get lost.
Okay. So presumably that is kind of driving this asymmetric attention then.
Yeah.
Okay.
Yeah. It might be that however it learned, and again, this is a toy model,
right,
that it's going to tend to pay attention to whichever one came first, as opposed to whichever one's most recent. You can imagine those are the two most likely, right? Either the first one or the last one.
The most recent one. Yep.
Yeah.
Okay. Thank you.
All right. So we'll keep going. You guys are asking great questions, but this is the key pattern, which if we get to it, basically they're going to talk about if you can do this and you can have multiple layers and you can compose these types of patterns, then essentially you can build any pattern you want.
And in each of those cases, it was attending to that token. So it's copying the ers to the ers, and then we have this hypothesis that maybe somehow the way it's doing that is because the previous copy of D, or the present token is D, and that was the token that preceded where we attended.
Johnson, why are you naked? Because my t-shirt sucks. Look at Gibson. He's wearing a true classic tee.
So we'll call that the induction pattern. And we can actually verify our hypothesis that that it's actually looking for the fact, it's sort of that the fact that the previous token is the same is what it's looking for. And if we just look at how the key for this, so let's pick a particular case. So where we're on pot and it attends to ters. Well, it turns out that if you look at how the key is computed, the key isn't computed from the present token, but it's actually computed from the previous token. So we grab the content of the preceding token and inject that into some subspace and then use it to construct our key. Whereas we construct our query mostly from the present token. And so by going and looking to go and match the present token with the subspace that we stored this in, we're able to go and look for tokens that follow a token that matches the present token. So that's a little bit more of a complex algorithm than anything we've seen. It's almost a little bit like nearest neighbors, in that you're searching for you're almost treating your text up to this point as being a little bit like a training set, and you're looking for places where there's a match, and then you're going and copying that or something. Now, it does other interesting things too. So, sometimes it's just the present token that matters, but there's also cases where, like here, we have this D, and if you look at this, I don't have it here, but if you interactively play around with this, you'll see that it really is that the D of this query matches the D of this key, and the Mr. of this query matches the Mr. and to a lesser extent the Mrs. portion of the key over there. And so they match, and then that causes us to attend to ers, which then increases the probability of ers. So it really is this copying thing, and we're calling that general mechanism of looking for the token that in the past has preceded your present token, looking for situations that were analogous to your present situation, and then predicting that whatever happened happened next in the past is what's going to happen next now. That's what we call induction, or an induction head, and that seems to really be the kind of the workhorse of meta learning in a lot of transformers. And we see it.
Oh, I don't know if he was done.
In large models, and it seems to be playing a big role.
All right, that's what I was trying to do, catch it before we went to the next screen. All right, so I want to make sure you guys understand this diagram, because this diagram is, like I said, this is the beauty of the research that they've done. What they're saying is, remember, the residual stream has a lot of floating point numbers in it, okay? I don't know what they used for this toy little model, but let's just say it's 128 floating point numbers, okay? And it doesn't actually work this way, but I'm gonna give you a mental model that's simpler, okay? So imagine that when you embed each token, each word, what it does is it puts floating point numbers into the first 32 of those 128 positions, and it leaves the rest, the other 96, all zeros. Okay? Now the first attention head can come along and it can say, ah, I see a D, so I'm going to copy D into positions 33 through 64 on the residual stream. Okay, so what I've done now is I've basically set, so the word ERS might still be in the first 32 floating point numbers, but now basically the word D is in the next 32 floating point numbers. Okay, so this token position, because the residual stream has a lot of capacity in it, has information not just about the current token, but it also has information about the previous token in a specific location on the residual stream. So what can happen now is the second attention head, rather than looking at the first 32 floating point numbers, which would be looking at the current word, can say, I know where to look. I'm going to look in floating point numbers 33 through 64 because I don't want to know, is the current word ERS? I want to know if the previous word was D, because I'm a D. I'm looking for a previous copy of myself. So if you have in layer 1 an attention head that says, copy yourself into a special place in the residual stream in the next token, then that means that any transformer in a later layer can say, I want to attend to the token that comes after fill in the blank. If it's looking for itself, if it's looking for a noun, if it's looking for a verb. So does that make sense in terms of how by combining two attention layers, now you can get this really cool, and again, this only can happen if your residual stream has sort of like extra capacity for scratch pad, writing of stuff into there.
It does make sense. And I was going to say the last statement that you just made, that the only way it can scale for more layers and more attention heads is by scaling the dimensionality for each token representation, which is exactly what it is. Yeah.
Yeah, and in fact, in a previous week, I think Roger and I had talked about this, and when I was scanning over, I actually found that they explicitly say it in the paper. I don't know if I can find it. No. So they did a test to see whether or not the token embeddings were using up all of the residual stream, and they found that the token embeddings and the unembeddings mostly interact with a relatively small fraction of the dimensions. And so if I hover, you can see this footnote. What they did is they did a PCA analysis, and so then they found that the X number of the principal components were really big, but that basically after a while they petered out. And that means that there's a ton of unused space in the residual stream when you just are immediately after the embedding. Before you've done anything, no attention, no MLPs, all you've done is embedding. There's a lot of empty space in this. I called it 128 dimensional. I don't remember exactly what they used for this toy. So now again, I said the first 32 floats have numbers, the other 96 are all zeros. It's probably not that clean. It's probably rotated, but the PCA will handle that. It'll look to see, what you need to span the space of the embeddings, regardless of whether they're aligned with our floating point numbers or if they're just, in a slight rotation or whatever. But so they explicitly did check for this, because something I was thinking, oh, I could do an experiment, wouldn't be that hard. But now I don't have to because they already did it.
So Ted, that determines the kind of the subspace, the dimensions of the subspace associated with the embedding and unembedding.
Right. And so everything that's in the null space of that means that's free scratch pad space for all the MLPs and attentions to write intermediate work.
Do you know, did they do any analysis of kind of how the rest of the subspaces might be allocated or
Not
used
that
or
I've
anything like that?
noticed, but like
Okay.
I only just noticed this footnote
Yeah,
upon
yeah,
this
yeah.
reading, so it's possible there's more notes.
Cool. But the
But-
methodology is there. Yeah.
Yeah, and I can imagine, Roger, as the number of layers and attention heads increase, right? Those virtual induction heads, those are multiplier effect from layer 1 to layer 2. So it's, let's say in that example, it is, how many did they have? 12
In this
heads
toy,
and,
they did 12 multi-headed attention, yeah.
right, so the virtual heads will be 144 after 2 layers. Is that what it would be, or whatever that number comes out to be, right? So, and now you do, let's say 8 layers is 12 power 8. That's a huge number, right? Millions of attention heads. So you're not going to have those many dimensions. So of course, I mean, a very quick and dirty analysis is, well, you are, you know, you have less number of dimensions than the number of induction heads that can play an effect on your analysis. But more often than not, you know, the semantic analysis is limited in each sentence. So you may not need those many all the time, but then the question arises, why do we need those many induction heads? I mean, those are good questions to research and figure out where it leads to. The other thing that I mentioned that in some of the context also in the past, that excuse me, the quantization work that you also pointed out, QLoRa, which is this 4-bit quantization. There, in his analysis, Tim Dittmers did find that there's a single dimension of a single layer at any point in time that suddenly clicks. And that's the word that it's pointing to. It's just one dimension. And which is what these guys are also pointing towards. So it's kind of, you know, all those theories are aligning in the same way, same direction, and all the research is kind of pointing how the transformers are working.
Yep. Yeah. Yeah, go ahead, Jay.
I was wondering how far apart the two potters are, you know, the one on the right and the one on the left.
I'm guessing they probably only did like 1024 sequence length for this toy model. So they have to be within 1,000 tokens of each other. But, you know, he probably did somewhere around 500, 1,000 tokens, just like the first page or two of the book.
Okay. Okay, thanks.
But I think they purposefully picked something that they knew would have certain repeated words.
Yeah.
Like Potter and Dursley and stuff like that.
Yeah. Yeah. Yep. Cool. Thanks.
So he didn't show the numbers. He just said, take it on faith. But it turns out that the first layer transformer that shoves the D into some empty space on the residual stream is shoving it in a separate place from where the mister is getting copied into the residual stream. That's how this D can attend to that D, but this mister can attend to that Mr. and Mrs. And so it's entirely possible that if you removed this mister, then this attention, this red wouldn't be as strong. It might still be there, but it would be only half as strong. Or vice versa, if you had the mister but not the D, then it would be not as strong. So quickly you can see this idea of I'm going to copy something for the next attention layer to use can be composed in all sorts of ways. I've identified the subject of the sentence, so I'm going to put some information in a particular place that lets other people know that this is a subject. I'm going to put something that says this is a verb. I'm going to put something that says whatever, you know, that kind of stuff. And so then, now that we kind of got that out, the crazy thing is that if you think about it, it's not doing it in a hard-coded way, like the pattern for like, if you see a noun, look at the next word, that could be like hard-coded. But this, how would it know to look for a Mr. and a D, right? It's like, so it has to be that there are these sort of generic rules that can find patterns in the text, stash them away so that later on you can see whether or not that pattern repeats or whether or not you can utilize that pattern. So that's the thing that's kind of wild about this.
Hey, Ted.
Yeah.
When you're doing that, like you use the example, Mr. and D as two separate kind of attention heads, right? Within one layer. It's only a linear combination of those two that you can achieve, right? You can't do like an AND operator or something like that. Is that right?
Right. So, but like, to use my previously made up example of like which floating point numbers, right? Maybe the Mr. got copied to floating point 33 through 40, and D got copied to 101 through 110. And then because there's a projection going into attention, this thing could say, I want you to pull floats 33 through 40 and 100 through 110 and give those to me as, one block. And then on the key, I'm going to do certain things, and that's where you do the dot product to get your attention scores. Okay, so the cool thing is the projection in and the projection out means that you can choose from any part of the residual stream you want to your query.
Yeah, I see that, and maybe I'm just not following correctly here, but I can see where you can get kind of a multiplicative type attention when you have multiple layers, but within a single layer, it seems like you only get kind of additive linear combinations. I'm
not sure if I'm following you. I'm pretty sure what you're saying is right, but I'm just not necessarily like tracking with your train of thought. But like if you look at the Q matrix, okay, when you do multi-headed attention, on one side, the matrix is as big as your residual stream. So you can pick from that. And then in the other, it's just whatever your hidden QK size is, which is by default, everybody uses the residual stream divided by the number of heads, but technically you don't have to. Okay. So because that's the matrix and it's full rank with whatever your hidden QK dimension is, you can copy anything you want anywhere. So in the first position, you could copy any of the 128 floats that are on the residual stream. And in the second, you can copy any one of those, including you can repeat. You can copy the same one multiple times if you want. Okay. So hypothetically, if it wanted to, and the D info was somehow encoded in floats 101 through 105, it could copy that 4 times over if it really felt like it. I don't know, but so it's not even just that you are copying those, it's also you can choose where you want to copy it into your hidden dimension. And so if you copy it into positions 1 through 5, and the key copies some corresponding information, unless it copies it in 1 through 5, they're not going to dot together.
Right.
Yep. So I'm sure what you're saying is right, but I was just trying to say that you really have fairly selective choice of what part of that hidden QK dimension you put things, where you put them, so that they will have the opportunity to align and give you really large attention scores.
Also, I don't know if it was already discussed. I'm sorry, I may have lost track. But someone asked this question, or mentioned how D is being affected by Mr. in this case, and the bottom right, and it also depends, where we are in the stage. Like, is it in the inferencing time we are trying to figure this out, or in the early stages of training? Pretty sure in early stages of training, what we see here is not the pattern that will be observed. It could be just copying the previous token again and again, as you mentioned. But if it's all trained, then it may have already been trained on multiple instances of Mr. and Mrs. someone else. And then it knows that, well, this is how it has to attend to.
So I don't think we're going to have time to finish up this video and really kind of like go through everything. But the thing that I like about this work, and that I partly, is that it does give me some mental models to think about what's going on under the hood in the transformers. But also, like, just again, I said this before, I'm going to repeat myself in slightly different words, that I highly doubt that this transformer has a particular hard-coded thing that it's looking for the word D and looking for ers and looking for Mr. That it has some types of generic rules that do things like copy this information to the next token, so that in general, anytime you want, somebody can attend to the information of, you know, the token that comes after something, and copy this kind of stuff and copy that kind of stuff. And so the net effect of that is that these generic rules will recognize patterns in the context that's to the left of whatever the current token position is. And ultimately, this, again, remember, this is GPT. It knows nothing about what comes after it to its right. It only knows about the universe to its left. But eventually, we've trained these large language models sufficiently that they have some really strong pattern matching abilities, such that when to the left it says talk like a pirate, that fundamentally alters all the logits from then on, that the probability of it saying R and matey and all that shoot way up, just because that pattern appeared somewhere to your left. So that's the crazy thing, is that these patterns are not just simply like, I'm going to look for the word white and see if the word house comes after it. I'm going to look for base and see if ball comes after it to know it's baseball, or basket and ball, basketball. Somehow the aggregation in these large models of these rules allows it to have much, much broader pattern matching rules. And it can basically, empirically, looking at GPT-3, GPT-4, it can compose patterns. So you can say, talk like a pirate, only use short words, you know, instead of regular sentences, output them like JSON, and it'll actually compose all three of those instructions. And it'll affect all the probability of the logits that come later, because you gave it those three things in its prefix. That's, to me, the super gnarly thing, is that, yeah, anybody could just hard code like ImageNet, like, oh, this is the pattern for what a dog is. But we're not just doing that. We're well beyond that kind of hard coded, this is a dog. Now we have complex language patterns that we're able to compose. And even if you are still in the camp of that it's a statistical thing, it is a pretty just crazy advanced ability to layer those kinds of statistical things when you give it different kinds of language and instructions on its left.
Yeah, and then the title says, you know, exactly what you were saying, Ted. It's the workhorse of meta learning. Like, it, as you said, it's not that it's focusing on Mr. and Mrs. Like, depending on the prefix, it has figured out, well, I have to now, like in some cases, yes, it knows about pirate language and JSON and other thing. But when you give the in-context learning, then it's learning to learn more pattern and then apply it.
Yeah, and so that's the part we're not going to have time to get to, but that this is ultimately meta learning. So Walter had a very good point, right? So it could be that, like, Potters is actually in your training corpus, and so it kind of knows to expect ters after the word pot, right? But like, if you've heard of like Pig Latin, where you whatever, stick the vowel at the end of the word or whatever, you can make up your own made up language where you scramble the letters and try to think of something that you think likely has never appeared in the training corpus, okay? Where, you have to you have to put the first letter, at the end, you have to triple it, and then you have to take the first vowel and stick that at the end, whatever. And that's the rule for how you have to talk from now on. And then you tell GPT-4 to do it, and it'll do it. Dog will somehow become og triple D-O, and, tree will become R-E-E triple T-E, and it'll just follow the rules. It might make mistakes, but that's just super powerful meta learning. It's not just hard-coded rules based on the only words that it's seen and only the sequences of words in that particular order that it's already seen.
Yeah, the only thing that it has not learned or meta learned is how to count it, because of the tokenization that it does. So if you tell it how many words are there in my sentence that I'm going to write next, and boom, you never know whether it will give you the right answer or wrong answer.
It does struggle with counting words, counting letters, and things like that. Like ChatGPT 3.5, I just said something like, name colors that don't have certain letter or that do have a certain letter, and it would make mistakes on something. But again, we know behind the scenes it's tokenized, so it's less surprising there. All right, James, you've been very patient. Sorry. Thank you for having your hand up.
No worries. Since you're stopping, I thought I would ask a question or your plan. So in the first example there is a thin line on the. You can see that, right? And so it's kind of similar to the Mr. D in the bottom.
Yes.
Right?
Yes.
And
they're saying some amount of the attention weight came from the being placed into this token position. By the
and then if you go, and if you go to the left, there's probably a very light green going to the before Potter's, but I guess we just can't see it.
Yeah, I can't tell. There could be. I feel like maybe I see it. I feel like maybe I see it, but yeah, it's hard.
Okay.
But so you can imagine that the pot, especially, I don't know if it is case sensitive or not, but like the pot is much more likely to be Potters than just any pot, because there could be other words that got tokenized, potential, whatever, right? So it does make some sense that the would sort of increase the likelihood that it's Potters and not some other word that just happens to begin with POT.
Yeah, cool. And in the earlier, even in this video, the previous video, they talked about the bigram, with the zero level attention. Is any of that happening with the Mr. D or the pot? Or
I don't know, and I don't know how much that goes away once you get to really large language models. I would have to think that for something as sophisticated as even GPT-2, bigram statistics don't buy you very much.
Okay.
Right.
And I think overall they mentioned, right, in one of the earlier slides, how many nats of information loss contributed to that. So I think it was still non-significant, at least in that simpler analysis.
Yeah, I'm not sure, because I'm not sure how good their toy 2-layer model ever got. So, but I just wanted to show you. So if you I think we're gonna stop the West Coast Machine Learning meetup discussion about this. If you want to continue, you can actually read the article. You will see certain diagrams where you can pick like a particular attention head, and then you can look for where the pink is and where the output values are strong. And this is the example where they did gibberish. So they didn't even bother showing you what the letters of the different tokens were. They just said, this was token 21,549, and then token 15,231. But you'll see that, like, for example, 21,549, 15,231 repeats. There's a 21,549, 50, right? So they made sure there were repeats, even though it was just gibberish tokens. And you can see some of the other articles, but they have these type diagrams. I found that this little square on the left that shows you where the attention is stronger and weaker, I found it very difficult to read that diagram, just to warn you. But they have a whole bunch of them in there, and so they kind of go into that, and then there is a follow-up article. Chris wasn't the primary author on that one. Catherine was, and this one they then did bigger transformers. They didn't try to do the math, so there's no more QK, OV, or whatever. They just tried to look to see where the attention patterns are actually happening and stuff. And so if you look at this article, then you will see things like like these, they do these tests, okay, where they say, we're going to look at this induction head pattern, and we're going to see that certain weights happen in certain places when we have an induction head. And so they figured out a way to interfere with those weights. I don't remember exactly what the scheme was, but so they said, we'll train this thing, and you'll notice this really funny thing happens when you're training. You look at the weights, you inspect the weights, and you don't see induction heads, and the loss is high. And then at a certain point, you start seeing the pattern. These are induction heads, and the loss drops dramatically. They literally call it a phase shift, okay? Just like in chemistry, when you like melt ice, right? The temperature, it decreases, and then there's this phase shift part. So then they did a bunch of experiments around this, where if they messed with the induction heads, then it caused that phase shift to happen later. And then I think if they let it train, but then they zapped the weights where the induction heads were, it caused dramatic decreases in performance. So they have a number of arguments here where they basically really looked at these induction heads to say that there's this really set of powerful correlations between better performance when you have induction heads, worse performance when we mess with them, et cetera, et cetera. Therefore, in-context learning is happening via composition of induction heads. That's the general gist of this second article. So they sort of say, what's the strength of the evidence for these different things? But they have these cool diagrams. So this is the one where you're going to see in this yellow region, this is where they're talking about the actual the phase change. Okay, so you'll be moseying along, and then blammo, you'll have a sudden massive change in loss, and then you'll kind of mosey along much flatter. And then they, like I said, they do things where they can cause it to happen later, and they can do whatever things. But you'll see diagram after diagram after diagram where they've highlighted a certain yellow region, and they're basically saying, look, you see on this one particular PCA plot, things are moving down to the left, and then in the yellow region, they change direction. And then once you leave the yellow region, they change direction again. So it's like all this evidence that points to that specifically induction heads and this period of formation of induction heads is where in-context performance dramatically improves and originates. So diagram after diagram after diagram, you'll just see this little yellow stripe. And they're saying, here's all our evidence that this yellow stripe is when the smart stuff begins happening, and it's correlated with the induction heads. All right, so I think we'll pause here in terms of the formal presentation and the walk through the Anthropic stuff.